Hello everyone, I am Satbir Kaur, a PhD student in HBNI BRC Mumbai, also an alumni of University of Mumbai from the batch of 2014 to 2016, and I'll be taking commons in nuclear physics. I'll be starting with the basic properties of nucleus. These are the topics I'm going to cover with one question each, and similar questions are there in quiz also. One of the lectures already taken by Vivek Parker sir earlier. So starting with the first property, that is the nuclear size. Now there are different ways to measure the nuclear size. One of it is using mirror nuclei concept. So what is a mirror nuclei? Two nuclides that have same mass number but the number of protons in one is equal to the number of neutrons in other is a mirror nuclei. For example, 11 boron and 11 carbon. Here we see that 11 boron has number of protons 5 and neutrons 6, whereas 11 carbon has number of protons 6 and neutrons 5. So it is a mirror nuclei. And if we compare the binding energies of these mirror nuclei, it is observed that the total binding energy will not be equal because of the mass difference due to neutron and proton mass and difference in the Coulomb energy. And if we consider the nucleus as a sphere of uniform charge distribution with radius r and charge q equal to Ze, then the charge density is given as rho, which is charge upon volume of the sphere, and we get charge in terms of r. Now we can calculate the Coulomb energy using Gauss theorem from electrostatics as this. So on substituting QR and its differentiation in this integration, we get Coulomb energy as 3 by 5 Z square E square by 4 pi epsilon naught R. So for a pair of mirror nuclei with charges Ze and Z minus 1 E, we get the difference in the Coulomb energy as this formula. And on solving further and substituting R as R naught A raised to 1 by 3 in this equation, we get the difference in the Coulomb energy proportional to A raised to 2 by 3. So if one knows the Coulomb energy difference and the mass number of the nuclei, we can calculate the radius or the nuclear size. Using this concept, a question was asked in CSI NET exam. The difference in the Coulomb energy between these two mirror nuclei is 6 MeV, and E square is approximated to 1 MeV Fermi, and we have to calculate the radius of one of the mirror nuclei, that is 49 manganese nucleus. So the solution is, now from the previous slide, we know that for a pair of a mirror nuclei, the difference in the Coulomb energy is given to be this. Or one can also write this. So on substituting the difference in the Coulomb energy and the mass number, one can calculate the radius. So mass number is given to be 49 and the difference is 6, and approximating the value of E square, that is 1 MeV Fermi, we can calculate the radius and it comes out to be 4.9 into 10 raised to minus 15 meter, which is option B. Okay, so next property is the nuclear density. In set exam, it was asked to calculate the nuclear density of 197 gold, where the mass of the gold is given to be 3.2707 into 10 raised to minus 25 kg and R naught as 1.2 Fermi. So the solution is nuclear density is nothing but nuclear mass upon nuclear volume, and nuclear mass is given as mass number into mass of a nucleon. Nuclear volume is written as 4 by 3 pi r cube, where R is nothing but R equal to R naught A raised to 1 by 3. So substituting the nuclear mass and volume, we get the nuclear density as this. So if you see, nuclear density does not depend upon the mass number but depends upon the nucleon mass and R naught. which are constant. So the nuclear density is always constant and is taken to be 2.29 into 10 raised to 17 kg per meter cube approximately. So if you see, it is close to option A. So option A is the correct answer. Instead of solving with the mass given of the whole, one can directly mark option A. Another property of nucleus is nuclear angular momentum or nuclear spin. The nucleus is an isolated system and has a well-defined nuclear spin. Each nucleon in a nucleus, that is protons and neutrons, have orbital angular momentum L and spin angular momentum S. According to quantum theory, orbital angular momentum is an integral multiple of h cross, while spin angular momentum has a magnitude of half h cross and has two states, parallel, that is plus half h cross, and antiparallel as minus half h cross along a given direction. Total angular momentum for each nucleon is J equal to L plus or minus S, and total nuclear spin J is the summation of total angular momentum. So if mass number A is even, then J must be an integer, and if A is odd, J must be half integer, and all nuclei with even N and even Z, that is even number of neutrons and even number of protons, have J equal to 0. Next nuclear property is parity, and parity refers to the behavior of wave function, that is psi, under inversion of coordinates through the origin. Now if x becomes minus x and wave function sign does not change, then the parity is said to be even or positive. And if the sign of the wave function changes, then the parity is said to be odd or negative. So in general, in quantum mechanical notation, all particles are eigenstates of parity, where p is equal to plus or minus 1. P can be taken as quantum number. P equal to plus 1 means even parity, and p equal to minus 1 means odd parity. We write nuclear states with nuclear spin along with parity as an example here, 0 plus, where nuclear spin is 0, that is J equal to 0, and parity is even parity because it is positive. Now the parity of a nucleus is the product of the parities of all individual particles or the nucleons, and can be written as this. And parity of a single proton or neutron is given as this, that is P is equal to minus 1 raised to N. The important thing that decides about the parity is the orbital angular momentum L. Now for odd mass number A, the parity is given by the unpaired proton or neutron as in nuclear shell model, and parity is conserved in nuclear process. Next is the nuclear shape. Now nuclear shape can be deduced by measuring its electromagnetic moment. Nuclear moments give information about how a magnetic moment and charge is distributed on the nucleus. So the two important moments are electric quadrupole moment represented as Q and magnetic dipole moment represented as mu. The next nuclear property is quadrupole moment. Electric moment depends on the charge distribution inside the nucleus. Generally, it is assumed that the nucleus is spherically symmetric, and hence the charge density rho is a function of radial coordinate r dash only. An electric potential of charge element dq is located at an r dash, that is here, and is given by V of r is equal to this. So using Legendre polynomial and on multiple expansion of this potential, we get V of r as this term. Here the electric moments are the coefficient of each successive power of 1 by r. So the first one is called the monopole term. It has charge but no shape information. Second term is the dipole term. It is always zero because of definite parity. While the third term is the quadrupole moment term. And it is interesting because this moment gives the measure of deviation from the spherical symmetry of charge distribution. And it can be written as this along the z direction. So the formal definition of electric quadrupole moment can be written as this, while the spectroscopic notation of quadrupole moment from the shell model is denoted as this, where the root mean square of radius is equal to 3 by 5 r naught square raised to 2 by 3. Units of quadrupole moment is meter square or bars. So for a spherical symmetric nucleus, electric quadrupole moment comes out to be 0 as one can deduce from here. So all j equal to 0 nuclei have quadrupole moment 0 by for q greater than 0 we have a prolet shape, and for q less than 0 there is an oblate shape of the nucleus. So a question was asked in CSI NET exam where they have said to calculate the quadrupole moment and the units of Barn of 27 aluminium nucleus and shell model. So 27 aluminium has Z equal to 13, and from shell model configuration J comes out to be 5 by 2. And using the spectroscopic notation of quadrupole moment, that is this as from previous slide, and on substituting the value of A, J and R naught, we get Q equal to 4.4 into 10 raised to minus 30 meters square. Now since one barn is equal to 10 raised to minus 28 meters square, so Q becomes 0.044 barns. So the correct option is option A. Another property is the magnetic moment. We all know that when a charged particle moves in a closed path, here an electron in a circular orbit, it produces both angular momentum and magnetic field. So for a magnetic field located at large distances can be described due to the magnetic dipole moment located at the center of a current carrying loop, and is written as magnetic moment is equal to current into area, that is I into A. And velocity of the charged particle can be given as this and angular momentum as this. So on solving further, we get that the magnetic moment is nothing but proportional to the orbital angular momentum. So for electron orbital magnetic moment, we have mu L is equal to mu V into L upon H cross, where mu V is nothing but the Bohr magneton, which is equal to E into H cross by 2 times mass of electron. So for proton orbital magnetic moment, mu L is nothing but mu N times L by H cross, where mu N is nothing but nuclear magneton and is given as this. So nuclear magneton is 1836 times smaller than the Bohr magneton of the electron. In general, the orbital magnetic moment can be written as this and spin magnetic moment as this. So the values of GL, GS and mu for respectively for proton and neutron is given in this table. As you can see, the magnetic moment for neutron is negative, which means it aligns antiparallel to the magnetic field. One can ask a question that although the charge of neutron is zero, there exists a non-zero magnetic moment. Why is it so? So the reason is neutron and proton are not the fundamental particles. That means they are the combination of quarks which consist of charge as shown here. Therefore, the neutron has a non-zero magnetic moment, and negative magnetic moment indicates that it has a tendency to align antiparallel to the magnetic field. So we know that the nuclear magnetic moments arise from intrinsic spin magnetic dipole moments of the protons and neutrons and the circulating currents, that is the motion of the protons. Now the nuclear magnetic dipole moment can be written as this. It is summed over all proton and neutrons, or can be written as mu equal to Gj mu n j, where mu n is the nuclear magneton, J is the total nuclear spin, and Gj is called the nuclear G factor. G factor may be predicted using the nuclear shell model, and it is analogous to Landé G factor in atoms, which is given as this. Now all even nuclei have magnetic moment 0 since the total nuclear spin is 0. So for shell model, we know that the odd nuclei, we consider only the unpaired neutron and proton. And for even odd nuclei, one has to only find the orbital and intrinsic component of magnetic moment for single unpaired nucleon. Now from spin orbit interaction, we know that J is nothing but L plus or minus S, where S is nothing but half. So in nuclear physics, higher J values lies below the lower J value. So for higher J, that is J equal to L plus half, magnetic moment is given as this, and for lower J value, that is J equal to L minus half, the magnetic moment can be written as this. Based on this concept, a question was asked in NET exam where we have to find the nuclear magnetic moment of 27 aluminium nucleus according to the shell model. So 27 aluminium has Z equal to 13 and N equal to 14. So the only single unpaired nucleon is Z equal to 13. And the last one is in higher J value, that is 5 by 2. So J is equal to 5 by 2, L is equal to 2 since it is in the D state. So the magnetic moment is given as this for higher J value, and it on substituting the value of J, that is 5 by 2, and Gs from the table I have shown earlier, we get mu equal to 0.793 times nuclear magneton, that is option C. Next is nuclear force. Nuclear force binds the nucleons in a nucleus. It is the strongest and short range force. It can be expected from the binding energy against mass number plot, which is constant at approximate 8 MeV per nucleon, whereas the binding energy of an electron in an hydrogen atom is 13.6 electron volt. Therefore, the nuclear force is stronger than the electrical force. Also, nuclear force is often called the strong interaction because it is the strongest of all the 4 basic forces, as you can see from this table. And this table gives the relative strength of these 4 forces. Now, one of the property of nuclear force is the charge independence. So why charge independent? Nuclear force is nearly independent of whether the nucleons are neutrons or protons, as it is a strong force, while charge plays a role in electromagnetic interaction. The nucleon force is same irrespective of whether the nucleons are protons or neutrons, once the Coulomb repulsion has been taken into account. And this can be confirmed by the study of mirror nuclei. Now, due to charge independence of nuclear force, masses, binding energies, when corrected for Coulomb terms, are very similar in light nuclei. And this can be seen in this table, where A is equal to 3. Suppose A is equal to 3, For tritium, total binding energy is minus 8.486 and Coulomb energy is 0. So the net nuclear binding energy is minus 8.486. And for helium-3, it is total binding energy is minus 7.723 and Coulomb energy is 0.829. So when the Coulomb energy is added to the total binding energy, the net nuclear binding energy is minus 8.552. That is similar to the tritium net nuclear binding energy. So this shows that the nuclear force is charge independence. Now another property of nuclear force is spin dependent. Consider a two-nucleon system, that is deuteron, diproton and dineutron. We know that the nucleons are fermions, so they obey Pauli's exclusion principle. That is, no two identical fermions can stay in a single state with same quantum number. Now deuteron has parallel spin state and can have total spin 1 and total spin 0 states. And the ground state of deuteron has nuclear spin 1, whereas for diproton and dineutron, they have antiparallel spin state and they violate Pauli's exclusion principle. So such systems do not exist. Therefore, we conclude that the nuclear forces are spin dependent and are attractive in nature for parallel spin but repulsive in nature for antiparallel spin. Now to study more properties of nuclear force, deuteron problem is considered. This table gives few properties of deuteron. Two important properties of deuteron related to nuclear force are magnetic moment and quadrupole moment. Magnetic moment of deuteron. As we have seen, deuteron has parallel spin state and lack of orbital angular momentum since J is equal to 0. So L is equal to 0 for S state. And this implies that the magnetic moment of deuteron should be simply the sum of magnetic moment of proton and neutron, which comes out to be 0.879 times nuclear magneton. So if you see, the measured value is pretty close but yet different from the value given in the table. This difference is then explained experimentally because of the admixture of L values. It was observed that 4% of its time deuteron is in orbital d state and 96% of its time deuteron is in S state. Now, since there is change in the angular momentum from L equal to 0 to L equal to 2, this indicates that torque must have act, and that is angle dependence is also there. Now, why P state is not admixed? As I said, in nuclear process, parity should be conserved. So, P state does not admix because parity is to be conserved. Now, quadrupole moment of deuteron. Deuteron has positive quadrupole moment, that is 0.2860 per meter square, measured with respect to spin axis. So the positive quadrupole moment indicates a prolate deformation with respect to spin axis as symmetry axis, or it is like a picture on the left and on the right. So positive quadrupole moment of deuteron indicates that the part of the nuclear force also depends on the spin and spatial part of the nucleons at the same time, which indicates that nuclear force is also a tensor force. And it is analogous to the classical force that occurs between the two bar magnets. So for deuteron, the force is repulsive when the spins are parallel and is perpendicular to the line joining the nucleons. And the force is attractive when the parallel spins are also parallel to the line joining the nucleons. So part of the nuclear force depends not only on the separation between the nucleons but also on the angles that their spin make with the line joining the nucleons. So from the magnetic moment of quadrupole moment, from the magnetic moment and quadrupole moment, one can say that the part of the nuclear force is non-central because of angle dependence and tensor in nature. So a question was asked in GATE 2012, which says that deuteron has only one bound state with spin parity +1, isospin 0, and electric quadrupole moment 0.286 per square. This data suggests that the nuclear forces are having. So from the previous slides, we can say that the option is D, that is spin dependence along with the tensor component. Okay, so next nuclear force property is that the nuclear force is also an exchange force. So according to the Yukawa meson field theory of nuclear forces, there exists a particle called meson or a pi meson. An exchange of this particle leads to the existence of nuclear force. So forces between the nucleons are due to the exchange of these virtual particles. By virtual meaning that the exchange particles only exist for a short time and is consistent with the Heisenberg uncertainty principle. So the pi meson can be of neutral charge or positive charge or negative charge. So force between a neutron and a proton exists because of the exchange of neutral meson between them. And when a pi minus meson jumps from a neutron to a proton, the neutron is converted into proton and the proton accepts the pi meson and then converts it into the neutron. And in converse case, it is the pi plus meson. So this indicates that the nuclear force is also an exchange force. Next, how do we estimate the mass of the nuclear exchange particle? We know the famous equation of Einstein that E is equal to mc square, where c is the speed of light. And suppose the exchanging particle is traveling between the nucleon at the speed of light. So nuclear force has a maximum range r, which is equal to speed of light into the time delta t, and delta t is the time required by the exchange particle to travel a distance r. So using uncertainty principle, we get delta E into delta t approximated to h cross. So from here we can get delta t in terms of delta E, and if we substitute this into this equation, that is the maximum range for the nuclear force, we get that the range is inversely proportional to the mass of the exchange particle. So on this concept, a question was asked in NET exam, where the range of the nuclear force between the two nucleons due to exchange of ion is given as 1.4 Fermi, and mass of ion is 140 MeV per c square, and also mass of the rho meson is 770 MeV per c square. It is asked to calculate the range of the force due to exchange of rho mesons. So from the previous slide, we have seen that the range of the, or the maximum range of the nuclear force R is equal to h cross c by mc square. So either one can solve it through this, where you get the answer on substituting the values, you get the answer 0.25 Fermi, or since we know that R is inversely proportional to delta E, so one can also solve it in this way. So the answer still would be 0.25 for me. So the correct option is option C. These are the references and important web pages I have referred to, and also you can refer. And the books that one can refer is the Nucleophysics by S.P. Patel and Kenneth Crane. Thank you.